Hi, let's go over another midterm from 2023. This is the second midterm from that year, and like other midterms in that year, it has 3 questions and 45 minutes time. So let's go over the first question. So in this question, we are given function f of x, and we are looking for a non-zero value for a, which for that specific a, f of x has a critical point that is also an inflection point. So one point is both critical point and inflection point. And we see a here and here. So the key to this question is what critical point is. Critical point is the point that the first derivative of the function f prime of x is 0, and inflection point is the point that the second derivative of 0 at that point. So let's find what is f prime of x and f double prime of x. F prime of x is the first derivative of the function, which here we see the function which is very simple, just several power functions. So we just apply power rule here. It would be 3x squared minus 6ax plus a, and the second derivative would be 6x minus 6a. To find inflection point or critical point, we set each of them equal to 0. Here we see that, okay, finding the inflection point, which means set this equation, is easier because it's not it's just a linear function. It's not a quadratic equation. So what we can do, we can just simply set 6x minus 6a equal to 0 and solve for x. So 6x is equal to 6a. As a result, x equal to a. So basically, x equal to a is an inflection point for this function. Again, regardless of what a is, that's true. X equal to a is an inflection point. But we want to find a in a way that that point, which is x equal to a, is also the critical point. So critical point is a point that makes the first derivative 0. So let's just write the first derivative, f prime of x. I'm just writing that again, 3x squared minus 6ax plus a. And if x equal to a wants to be the critical point, it should make this equation 0, which basically means f prime of a is 0. So let's just plug that into this equation. So what we get is 3 times a squared minus 6a times another a plus a is equal to 0. Simplifying that, we get 3a squared minus 6a squared plus a equal to 0. And let me just move these here. And can simplify that. 3a squared minus 6a squared is negative 3a squared plus a is equal to 0. And we can factor 1a out. So a times negative 3a plus 1 is equal to 0. So there are two ways. Either this is 0, which basically means a is 0, or this bracket is 0, which means negative 3a plus 1 is equal to 0. A is 0 is not acceptable for this question because they said find values of a which are not 0. So a equal to 0 is not acceptable. So this is the only acceptable solution. So let's solve that. So moving the negative 3a to the other side gives us 1 is equal to 3a. So a is equal to 1/3. So a equal to 1 over 3 or 1/3 makes this function or changes this function in a way that the critical point and the inflection points are the same points. So basically it's a point if a is equal to 1 over 3, at x equal to a, which is 1 over 3, both second derivative and the first derivative would be just 0, which means the inflection point and the critical points are at the same point. Okay, let's move on to the problem number 2. Here we are given a function, and we are not given a function like y equal to something. Cos of x plus y plus pi over 2 is equal to 4x. So because y is not very explicitly given, basically we call these type of equations implicit equation. And when we want to take the derivative of that would be implicit differentiation. In part A, they said find dx over dy in terms of x and y using implicit differentiation. Something may kind of might be a little bit different from what you have seen. They said dx over dy. Most of the time we see dy over dx. Kind of conventionally we see dy over dx. But it's not, everything is the same basically. Dx over dy, it's taking the derivative of x with respect to y. So let's take the derivative of these with respect to y, basically what you see in the denominator of these. So it would be, okay, so here you have cos of a function, so it would be chain rule. So the derivative of cos is negative sine, regardless of its derivative with respect to x or with respect to y, it would be same. Negative sine of x plus y plus pi over 2. And now that we took care of the derivative of cos, we multiply that by the derivative of inside of that, which means this part. Derivative of x with respect to y would be dx over dy. Plus, the derivative of y with respect to y, it would be dy over dy, which is basically 1. And derivative of pi over 2 with respect to y would be just 0 because that's a constant. With respect to anything, that would be just 0 because that is a constant. So this is the derivative of the left-hand side, and the derivative of the right-hand side would be 4 times dx over dy. The derivative of x is not 1. Don't make that mistake. Derivative of x is dx over dy because we are taking the derivative with respect to y. A little bit different from what we had past. So what we want is dx over dy, so let's isolate them. So we have one dx over dy here and one of them here, so we need to collect them on one side. The first thing is this is kind of stuck in this bracket, in these parentheses. So let's expand it. So by multiplying the sign of these to this bracket, we kind of free dx over dy from the bracket, and then we move it to the other side. So what I would get is negative sine of x plus y plus pi over 2 times dx over dy. And now I multiply these by the second term here, which is minus sine of x plus y plus pi over 2. And the other side we have 4 dx over y. And now I move and collect all the dx over dy on one side. So basically, I just move these term other side of the equation. So what I would get is negative, on the left hand side I would have negative sine of x plus y plus pi over 2. The right hand side would be 4 dx over dy plus sine of x plus y plus pi over 2 dx over dy. Now I can factor dx over dy on the right hand side. So dx over dy multiplied by 4 plus sine of x plus y plus pi over 2. And the left hand side would be simply as is, negative sine of x plus y plus pi. What I'm looking for is dx over dy, so simply I isolate that by dividing both sides by this term. So what I would get is dx over dy equal to negative sine of x plus y plus pi over 2 over 4 plus sine of x plus y plus pi over 2. This gives us the derivative of x with respect to y very implicitly. It's not in terms of x or in terms of y, it's in terms of x and y. So this is an implicit differentiation. And now they are saying evaluate dx over dy at 0, 0. So simply we just evaluate these when x and y, both of them are 0. So it would be, I just write it here, dx over dy at 0, 0 would be when I plug in 0 for x and 0 for y. So what I would get is negative sine of 0 plus 0 plus pi over 2 over 4 plus sine of 0 plus 0 plus pi over 2. And now what I get here is negative sine of pi over 2, which I highly recommend to memorize sine of pi over 4, pi over 2, 3 pi over 4, all of multiples of pi over 4. And the denominator would be 4 plus sine of pi. Sine of pi over 2 is basically 1, so I get negative 1 over 4 plus 1, which is negative 1 over 5. So negative 1 over 5 is basically dx over dy, or you may call it x prime, but it might be a little bit weird because we haven't seen that often, but this is dx over dy. And now as the second part of this, they said write the equation of tangent line to the curve at this point. So generally we write the equation of tangent line using a slope point form, which is y minus y1 is equal to m times x minus x1. Have that in mind that this m that we used to have here is dy over dx. It's not dx over dy. It is dy over dx. So what we have here is not this m. It is different. Or how can you do that? It's simply thinking that x and y's are swapped. So you can write it this way. X minus x1 is equal to m times y minus y1. And now this m here is what you have. This is dx over dy. And as a quick note, dx over dy, if you don't feel comfortable finding dx over dy, there is no problem. Just simply find dy over dx. Whatever you got, you just flip that, which dy over dx would be negative 5. And you flip that, it would be negative 1 over 5. So, but it's really helpful to be kind of feeling comfortable with taking the derivative with respect to any variable. So here, just have that in mind that I change the x's with y's, because what we are doing is taking the derivative with respect to y, so it's a little bit more consistent. So what we have here is x minus x1, tangent line at 0, 0. So the x coordinate is 0, is equal to m, which is now the slope that we found, negative 1 over 5, y minus 0. So its x is equal to negative 1 over 5 y. This is already correct. If you want, you can rearrange it. For example, you can say y is equal to negative 5x. Both of them are correct, and both of them are equation of tangent line to that curve at 0, Okay, so let's move on to part C. Using the answer from part B, use linear approximation to estimate the value of x such that this is on the curve. Okay, so basically they are saying approximate this x because we are doing linear approximation if y is this. Okay, linear approximation and equation of tangent line, they are same thing, they are identical. So I really doesn't matter which of these two you are using. I can use both of them, any of them you like. X is equal to -1/5y. So I want to approximate x at this y. So what I do, I just plug in this y here. I can say x is approximately, the actual x, this x, approximately -1/5 times 0.1, which gives you -0.1/5, or you can write it differently, like -1/50. Anyhow, you prefer to write it, or -0.02. This is an approximation for this x value. In this question, is everything's kind of changed. It seems x and y are swapped. So, or if you use this one, again, you just plug in 0.1 for this y here, and you solve for x, which gives you exactly the same thing. Okay, perfect. So we have that as well. This question is basically done. This question was very easy. Just the only tricky part was everything is kind of swapped, dx over dy. Okay, so let's move on to the problem 3. Take your time, or maybe if you want, you can pause the video to read the question, think about it a little bit, and then I will start to go over that. Okay, the information that we should get from this question, there are a bunch of maybe non-mathematical related uh, words here, like, I don't know, ideal gas. If you know what it is, that's good, that's maybe helpful, but really you do not need to know them. What matters is there are a bunch of variables here, like the pressure, the volume, and temperature. So P, V, and capital T, all of them are variables. And here they said N is the amount of the gas enclosed. Okay, it's enclosed, which means it's not changing. And R is the universal constant, which is also constant. So N and R are basically constant for this problem. N is the amount of gas enclosed. So if there is a leakage, yes, N would be different. But here we have a fixed amount of ideal gas. So the amount of gas is not changing. So N is constant, basically. Maybe in another question, N can be different, which means the number of molecules are changing. So P, V, and T are the only variables. And because the the gas tank that we are using is spherical, the V here is the volume of a sphere. And they already provided for us. And also we know the surface area of a sphere is also having this equation, 4 pi r squared. And now in part A, they are asking, suppose that we heat up the gas at the constant rate of 3K over S. What is K? If you know that, that's helpful. If you do not, that is Kelvin. Okay, that's 3 Kelvin per second, which basically this is a rate. It's a derivative. So basically they are saying that the derivative of temperature with respect to time, how I know it's with respect to time? Because it's per second. The derivative of time and temperature with respect to time is 3. And it's not -3. Be careful. They are saying heating up. If they said cooling down, it means temperature is going down, which means the rate would be, the derivative would be -3. So basically this word is controlling the sign. This is just magnitude. Okay, it's 3. And they said while keeping the pressure at the constant level 3/4 PA or Pascal basically. The pressure is constant. Pressure is 3/4. That is constant. Have that in mind. And what is the rate of change of the radius of the container when the surface area of a container is this much, 0.4 square meter? Your answer should be in terms of N and R. So we want to know rate of change of the radius. So basically they want to know how fast the radius is changing, maybe increasing, maybe decreasing. So this problem is a related rate. Why? Because they are providing one rate to you and they are asking for another rate. And the other rate is derivative of radius with respect to time, how fast the radius is changing. So before relating these two with each other, kind of finding this one basically, what I usually suggest is find the relation between T and R, the relation between the temperature and the radius. Let's basically, what is the relation? Relation is one equation that you have T and R within that equation. So what do we have? We have P is equal to nRT. This equation has T, but it doesn't have R. But we know that radius, how it impacts these. That will change the volume of the container. So let me just write this one as well here. So V is also 4/3 pi r cubed. If I kind of mix these two, what I get is P times V, which is, because it's a spherical container, 4/3 pi r cubed is equal to N capital R and T. Right now, what I have is a one equation which has R and T in that. The R for radius and the T, big T, for temperature. So it is basically the relation that I wanted. This is how I will relate radius, the rate of the radius, and to the rate of temperature. So now that I have it, I take the derivative of both sides. Take the derivative with respect to what? It's not radius, it's not temperature. It is with respect to time. So I take the derivative of both sides with respect to time. Don't forget that P in this scenario is constant. It has a value 3/4 Pascal. So when I take the derivative of this one, P is a constant, it stays there. 4/3 is a constant. Pi is a constant, so all of them stays there. And I only take the derivative of R cubed. And what is the derivative of R cubed? Do not forget that you are taking the derivative with respect to time, with respect to little t here. So it would be 3r squared times dr/dt. Why it's happening? Because of the chain rule. I'm taking care of the power as with the power rule, so that's what I see here. And then I take the derivative of the base, which is r, with respect to time, which gives me dr/dt. Now I have the derivative of the left-hand side. I write the derivative of the right-hand side, which n is constant, r is constant. The derivative of t would be dt/dt, the derivative of temperature with respect to time. So this is how I'm relating the rates, and this topic's name is related rate. Now I can use the values that I have. So let's see what values I know. I know P is 3 over 4. Perfect. I know 4 over 3 is constant, pi is constant. Everything here is okay. This is unknown, which it is supposed to be unknown because this is what I'm looking for. And on the right hand side, n and r, they are unknown, but they said at the end your answer should be in terms of n and r. So it's okay to have them as in the final answer. And dt over dt is also given to us, which is just 3. The only thing that I don't know right now is this r. And I'm not supposed to have r in my final answer because they said just these two are supposed to be there. So let's go back to the question and see how to find that r. They said they want to know the rate of change of the radius of the container. They want it when the surface area of a container is this much. So they don't want the equation generally, they want it at a specific point. At what point? When the surface area of a container is 0.4 square meters. So what is surface area of a container? This is the equation for that. So I know surface area of a container is 4 pi r squared. And I want to know what was the radius at the point that the area was 0.4 meters squared. I mean, I don't write the unit anywhere, so I just keep it like this. So here, from these equations, I know 0.4 is equal to 4 pi r squared, and here I can solve for r. So dividing both sides by 4 pi, I get 0.4 over 4 pi. So r is square root of 0.4 over 4 pi. Basically, what they ask is, what is the rate of change of the radius of the container when the surface area was this? Or basically, when the radius was this. They are same thing. Okay, radius is that, and now I'm looking for this when radius is this. So I plug in this radius here. So now what I get is 3 over 4. I'm just writing this one, just plugging all the values in. So 3 over 4 times 4 over 3 times pi times 3 times r squared, which is a square root of 0.4 over 4 pi squared times dr over dt, dr over dt. This is the left hand side. Let me just round. And the right hand side would be simply n, r, and 3. And don't forget that we are looking for this guy here. So let's simplify the left hand side a little bit. 4 and 4 get cancelled, 3 and 3 get cancelled. And yeah, so on the left hand side we have pi 3 square root, which is squared, so they cancel each other basically. So it gives me 0.4 over 4 pi times dr over d, and the right hand side is n, r, and 3. So I cancel this pi with this pi, and I divide both sides by basically this. I get dr over dt is equal to nr 3 divided by 3 times 0.4 over 4, which if you simplify that, you see that, okay, these 3 and these 3 get cancelled, and overall you would get n r, and that 10 is coming from these two when you simplify that. So this would be the rate of change of the radius with respect to time when the surface area was 0.4 square meters, or when the radius was this much. So quickly going over that again, before relating the rates, you relate the variables, the t and r. What does relating mean? It means having one equation which you see both of them in that equation, and everything else is basically constant. Now that we have it, we take the derivative of that with respect to what? To time. Now, after doing that, we just plug in all the values that we have. Okay, let's move on to the next problem, the next part of this problem. They said now, suppose that we keep the temperature constant. So this time the temperature is constant, while we are expanding the container in such a way that its radius is increasing at the constant rate of this. Okay, this time I know what the rate of radius is. So I know what is dr over dt is, which is 0.1 meter per second. And just have it here as well. T, the temperature is constant. So these are important information. They are asking what is the derivative of log of the pressure, log of P with respect to time, when the radius of the container is this much. Okay. So basically they are looking for d over dt of log of P at r equal to 0.6 meter. Okay. Before finding this derivative, we need to relate the radius and this. Let's first take this derivative. Let's see if we can simplify that. The derivative of this, okay, it's a complicated function, which is basically composite function. So we need to take the derivative of that using chain rule. Derivative of log is 1 over the input of the inside of that, which is 1 over p, times the derivative of inside, which is p prime. Or basically, it's better to write it as dp over the derivative of, the derivative is with respect to dt. So they are looking for what this is, basically. Let's see how we can find that. Again, I just write some of the equations that we have. Have p v is equal to n r and t, and we know t is constant, r is constant, n is constant, so all of them are constants. Basically, this side is totally constant. So I have the radius, the rate of the radius, and I need the rate of the pressure, basically. How to deal with this? What I'm gonna do, again, I develop a new equation which I have radius and pressure in that. So here, this is one very good starting point. So what I need to do is writing the v, or substituting v with the equation of that, which basically is 4 over 3 pi r cubed. Why it's helpful? Because it gives me a new equation which I have pressure and radius in that. 4 over 3 pi r cubed is equal to nRT. Now I have that. I take the derivative of both sides. Taking the derivative, but with respect to what? With respect to time. So I take the derivative of both sides with respect to time. The left-hand side is, okay, the left-hand side, this time p is not constant, it's variable. Also, you know the radius is also changing. We have the rate of that. So what we have here, or how we should take the derivative of that, is by applying product rule. So I have two parts, for example. I can say this part and this part. Some students call that f and g. And when you are taking the derivative of that, is you take the derivative of the first one, f, for example, it's p prime basically, which you can write it as dp over dt, which which is more precise, times the second one as is 4 over 3 pi r cubed, plus the first one as is times the derivative of the second one, which is 4 over 3 pi 3r squared dr over dt. We explained how it happened because of the chain rule. And the right hand side, what is the derivative of nRT? All the pieces on the right hand side are constants, so the derivative of that would be simply 0. Okay, now we have it. Let's see if we can plug in all the values. dp over dt, we don't have that. We don't have that neither, and you will see that we don't need that actually. Radius, we need this, and dr over dt, we also need that, and we have that. It is 0.1. Okay, let's see how we can simplify that. Do not forget that what we need is dp over dt times 1 over p. So I need these, and I need to have 1 over p beside that. So let's create that. So what I do, I just move these to the other side before plugging any value in. So what I get is dp over dt times 4 over 3 pi r cubed is equal to negative p times 4 over 3 pi 3r squared dr over dt. Because I'm looking for these, let's construct 1 over p besides these. How I do that, I divide both sides by p. Or you can think about that this way, that you multiply both sides by 1 over p. So if I, let's do it that way. If I multiply both sides by 1 over p, on the left hand side, I would get 1 over p dp over dt 4 over 3 pi r cubed, and on the right hand side I would get negative p 4 over 3 pi 3 r squared dr over dt times 1 over p. Let's simplify a little bit. I can cancel these 3 with these 3. I can cancel this p with this p, and anything else we can do. That's so far good enough. So again, we are looking for this. This is the unknown of this problem. The unknown was the derivative of these, which we took the derivative using the chain rule, and we got to that. So that's what we want to do, to find. So what we get is 1 over p dp over dt. Okay, let's isolate that. Basically dividing both sides by these p's. So on the right hand side, we already had negative 4 pi r squared dr over dt over this, which is 4 over 3 pi r cubed. Let's see if we can simplify that. Pi and pi get cancelled. R squared and r cubed, they cancel to just having r in the denominator. And instead of dividing by 4 over 3, you can multiply by 3 over 4. So we get these. That the left hand side is 1 over p dp over dt. The right hand side would be negative 4 dr over dt. There's one r down here, so it's over r. And instead of dividing by 4 over 3, I multiply by 3 over 4. And this way, cancel this 4 with this. Okay, perfect. I already know what dr over dt is. dr over dt is 0.1. I remember correctly, yes, 0.1 meter per second. And it is positive because they said the radius is increasing. If they said the radius is decreasing, it would be negative 0.1. And so basically on the right hand side, I have everything except, sorry, I have everything on the right hand side except this radius. How to find that radius? They gave us another piece of information. When the radius of the container is, okay, they want to know this derivative, this rate, which is basically this, when radius is 0.6 meter. So we plug in 0.6 into that equation. Just have that in mind that it is a common mistake that some people, some students plug in 0.6 here, or they plug that here. I mean, here it's okay, but here it's not okay. You can use that value, you can plug that value into your equation after you take the derivative, not before that. After you take the derivative, it's okay. You can just use that. If you plug that beforehand, before taking the derivative, your answer would be totally wrong. It would be 1 over p dp over dt is equal to, we got negative, there's a 3, there is a 0.1, this makes it 0.3 over r, and they said r is 0.6. If you simplify that, you get negative. Basically, d over dt of log of p, which we evaluated that, and it was 1 over p dp over dt is equal to negative 1/2. And this is the rate of change of log of the pressure when the radius of the container is 0.6 meters and temperature is constant. And also the radius is increasing at that rate. I hope everything here was clear and understandable. If you face any problem, feel free to check out learnforless.ca or reach out to me using info@learnforless.ca, and I try to be as responsive as I can. Take care and see you in another video.